Alright, it is the 9th of September 2025, approximately 9:36 p.m. So I'm going to attempt to do this thing where I have it, where I'm recording something to where I have the board right here, but post-edit I'll just flip it over to where this will look like it's right set up to you all, even though it's upside down by what's currently being filmed. So going back to the exercise questions for algorithm analysis here, we have the following question, exercise 2.2-2. Consider sorting n numbers stored in array A, open bracket, 1, n by repeatedly finding the smallest remaining element and swapping it into place it notes here selection sort. We are told to write pseudocode for this algorithm. And we are asked what loop invariant does this algorithm maintain? And why does it need to run for only the first n-1 elements rather than all n? And we're told to give the worst case running time of selection sort in theta notation. And we are further asked, is the best case running time any better? check the camera, see what that looks like. Looks fine. Okay. So, how do we go about this intuitively? Well, on pass I, we scan the tail to find the minimum and swap it into position I. After pass I, the first I entries are the I smallest in order. So what does that mean more rigorously, right? Well, let me just erase this here. That's a lot easier to erase. Just this little section of things, right, instead of the much bigger section. So let me see if the camera's still working correctly. Should be. Yes. Oh, is it? Yeah. Okay, so for the pseudocode of this, we have selection sort. Right, selection hyphen sort, open parentheses, a comma n, close parentheses, line 1. For I is equal to 1 to n minus 1. Second line, min id x, that is the index, is equal to I. Third line, for j is equal to I plus 1 to n. Fourth line, if the array a open bracket j close bracket is less than the array a open bracket min idx close bracket. Line 5, min idx is equal to j. Line 6, outside of the if statement, and the for loop, swap array a open bracket I close bracket, and I'll just write and because that's proper pseudocode. Array a open bracket min idx close bracket. So that's our pseudocode there for selection sort. Now, let's discuss the loop invariant. So, for loop invariant, at the start of each outer iteration, I such that, I is between, 1 is less than or equal to I, which is less than or equal to n. The prefix, array a, open bracket, 1 all the way to I minus 1, close bracket, consists of the smallest element smallest elements of A in non-decreasing order. And every element in the array A, open bracket, I dot 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 n is at least array A, open bracket, I minus 1. So at the start of each outer iteration, I, in which we have 1 is less than or equal to I, which is less than or equal to n, the prefix of the prefix array A, open bracket 1, all the way up to I minus 1 consists of the I minus 1 smallest, consists of the, I minus 1 smallest elements of A in non-decreasing order, and every element in the array A, open brackets, I, all the way up to n, close brackets, is at least array A, open brackets, minus 1, I minus 1, close brackets. So that's the loop invariant. See how this, well, let's look at this more explicitly in terms of initialization and the rest. So for initialization, for I is equal to 1, the prefix A, open bracket, 1, dot 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 0, is empty, which is to say trivially sorted and smallest. Okay, now what does that mean for maintenance? The inner loop finds the minimum of A, bracket I all the way to n, close bracket, and swaps it into A, into the array A, open bracket I, close bracket. So after the swap, the invariant holds for I plus 1. The termination is going to take up a lot more board space, so I'm just going to kind of freeze that and then erase it, and then we'll look at the thing, right? So. So determination when I is equal to n, the invariant implies the array A, 1 to n minus 1, is the n minus 1 smallest in order. So the last element must be the largest, ergo the array is sorted. Fair enough, right? So why only to n minus 1? Wrote the pseudocode. We stated what loop invariant does this algorithm maintain. We answered that. But why does it need to run for only the first n minus 1 elements rather than all n? Well, after placing the first n minus 1 elements, the nth is determined, right? Sort of this deterministic argument. This is more of a philosophical bit where it's like, well, think of such there's reasons why it could be wrong, there's reasons it could be right. Putting that aside, let's just talk about the argument in general. It says that, you know, try and think about like try and think about where you are right now as not being the result of the steps which previously happened, right? So it sort of works like that in a domino argument like sense, right? So after placing the first n minus 1 element, the nth is already determined. We don't really have to worry about that, right? So is the n minus 1 smallest in order, right? So that's roughly speaking why only to n minus 1. Now let's talk about the running time. It says give the worst case running time of selection sort in theta notation. So let's talk about the running time. Comparisons, let's see here. Comparisons are the summation from I is equal to 1 to n minus 1, open parentheses, n minus I, close parentheses, is equal to n times open parentheses, n minus 1, close parentheses, over 2, which is an element of all of theta of n squared. Swaps are n minus 1. This holds in the worst and also the best case. So it's similar to merge sort in that fashion, right? So the minimum search still scans the tail. So the best case time is not in fact better. Theta n squared. So we answered the other question, which is the best case running time any better, and that is no. It's like merge sort like that. So let's move on to the next exercise here. Oops. So exercise 2.2-3, we have consider linear search again because we went over it in 2.1-4. And so how many elements of the input array need to be checked on the average assuming that the element being searched for is equally likely to be any element in the array. How about in the worst case? Using theta notation. I just realized what I did on accident because I was about to say element in the assignment, but I wrote ASS, so the element in the okay, how about the worst case? Using theta notation, give the average case and worst case running times of linear search. And justify your answers. So intuitively, if the if the target is equally likely to be anywhere, you'll find it roughly halfway through on average, but sometimes you might need to inspect all n elements, right? So how do we say that a bit more rigorously, though? Well, let's let set x, well, let's let big X here be the index where the key occurs. Assume the probability that this event x is equal to I, a specific event, is equal to 1 over n, for I is equal to 1 all the way to n. So the algorithm checks exactly big X, it's supposed to be big X here, elements. So the expected value of x, which is big E, open brackets, x, close brackets, is equal to 1 over n times the summation from I is equal to 1 all the way to n of I, which is equal to n plus 1 over 2. So the average number checked is open parentheses n plus 1 close parentheses over 2, giving average time theta of n. It's the average number checked. So let's see here, what do we need? Input array, how many elements of the input array need to be checked on average? N plus 1 over 2, correct me if I'm wrong, right? So that holds up. How about in the worst case, though? So that the element being searched for is equally likely to be any element in the array. So we have the average time here of theta of n. Now, in the worst case, the key is at position n. I just realized that I can use this format for like chess videos and stuff. That would be pretty cool, right? Anyway, or absent if allowed. In the worst case, the key is at position n or absent if allowed, requiring n checks. Worst case time, then, would just be theta of n. Which, you know, there's got to be other cases where the average time does not equal the worst case time or the best case time, right? But in this case, it is that. So we have the average time here, worst case time here, the number of elements of the input array needed to be checked on the average right there. So we've answered this question fully. Now let's prepare to move on to the next one. The next exercise is 2.2-4. Let me just erase this here. It's got to be like some weird form of ASMR for somebody, right? I mean, I can't imagine listening to computer science and then, well, you never know. I mean, to somebody else, it's like the ASMR could be like listening to philosophy or something, right? It's like anything that you don't really care for, right? And then you can pretty much just label that as background noise, and there you go. Anyhow, exercise 2.2-4. So how can you modify any sorting algorithm to have a good best case running time? Well, intuitively, we want to be able to detect when the input is already sorted, or a pass makes no changes, right? And stop early. How do we say that a bit more rigorously, though? So, see it this way. Augment the algorithm with big O of n, pre-check, open parentheses, e dot g, for example, a single left to right, as I'm writing now, left to right scan, verifying the array A, open bracket I, close bracket, which is less than the array A, open bracket I plus 1, close bracket, for all I. Or an early exit condition within passes. For example, or an early exit condition within passes, like we mentioned earlier. So, for example, a no swap flag in bubble sort or halting insertion sort, immediately when no shifts occur during a pass. Close parentheses. There we go. So, right, interesting stuff there. Now, how about this? If the input is already sorted, so let's sort of look at this a bit more explicitly, right? So if the input is already sorted, the algorithm returns after big O of n work. So the best case time becomes theta of n, while the worst case and average case complexities remain unchanged. So it would essentially be like, okay, doing something goes bad, and it's like, well, correct, right? Doing something goes bad, correct. In a way, this is a rudimentary thing. Just to kind of think about it a bit more rudimentary. So yeah, and that pretty much explains well, the exercise asks, how can you modify any sorting algorithm to have a good best case running time? Well, that fully answers it now, doesn't it? It's just, there's many ways, I imagine, that this could be done. This is one, and it has fulfilled the qualifications. Well, the, what is it? The permissions, the circumstances, well, exercise 2.2-4 is covered anyhow. Check this. Okay. So erase this now. Oh no, it's my fingerprint, so you can know who I am now. Oh well. So, on to exercise 2.3-1. So it says, using figure 2.4 as a model, illustrate the operation of merge sort on an array initially containing the sequence right? 3, 41, 52, 26, 38, 57, 9, 49. Right. Which now I should show you figure 2.4. Looks like, well, there we go. Looks like this here. Okay. So what do we see going on there, right? So the intuition is to repeatedly split the array in half until singletons, then merge adjacent sorted subarrays back together. So let's sort of match exactly what figure 2.4 was doing there. Started out with, so figure 2.4 started out with A is equal to 12, 3, 7, 9, 14, 6, 11, 2. Now we want to go until eventually we divide to singletons. So we have the array, well, yeah, containing 12, 3, 7, 9, close brackets, open brackets, 14, 6, 11, 2, close brackets. From that, we can break these again. Open brackets 12, 3, close brackets, open brackets 7, 9, close brackets, open brackets 14, 6, close brackets, open brackets 11, 2, close brackets. From there, we can go to open brackets 12, close brackets, open brackets 3, open brackets 7, close brackets, open brackets 9, close brackets, open brackets 14, close brackets, open brackets 6, 6, close brackets, open brackets 11, close brackets, open brackets 2. And then from there we would merge pairs. So we have open brackets 12 operated with open brackets 3, close brackets, leading to open brackets 3, comma 12, close brackets. Also, we do the same with 7, 9, getting us to open brackets 7, comma 9, close brackets, and so on and so forth, right? All the way to open brackets 2, comma 11, close brackets, and this is what we have for the merged pairs. But we're not done here. Remember, we have to you have to keep on merging them until we get the list akin to being a whole list of the same number of elements as we started with. So let's look at merge level 2. We get open bracket 3, comma 12, close bracket, operated with open bracket 7, comma 9, close bracket, which leads you to open bracket 3, 7, 9, 12, 3, comma 7, comma 9, comma 12, close bracket. And we also have the case of open bracket 6, comma 14, close bracket, operated with open bracket 2, comma 11, close bracket, which leads you to open bracket 2, comma 6, comma 11, comma 14. Right. And at the end of all of this, there is indeed a final merge where you merge these two. What would you get for that? Well, you'd get the final merge, right? The final merge would be merge these two. So open bracket 3, comma 7, comma 9, comma 12. That operated with open bracket 2, comma 6, comma 11, comma 14, close bracket, to get you open bracket 2, 3, 6, 7, 9, 11, 12, comma 14, right? So I ran out of space there, but it's open bracket 2, comma 3, comma 6, comma 7, comma 9, comma 11, comma 12, comma 14, close bracket. So how would we do this for this case, right? So, well, replace each of these. So we'd have 3 over here, 41, 52, 26, 38, 57, 9, 49. Then, as you can see here, we break it in 2, right? And we'd go on and on and on until eventually we have the merged, the fully merged and sorted 3, 9, 3, 9, 26, 38, 41, 49, 52, 57. So what we should get for the end of this process here, you do the exact same thing that we did with this. So yeah, you just swap out these numbers here, right? So because it's the exact same number, which is of elements, which is very cool, which is very what's the word? Fortunate? Yeah, very fortunate for us. And you do the exact same thing until eventually you merge them all together and you got this here. So that's it for 2.3-1. So you can sort of argue, well, you didn't exactly show this more directly, but I'm pretty sure you can see this is more for pedagogical reasoning, you know, so, and we showed how this would exactly emerge, so it's fine by me. Let's move on to the next exercise. (2.3-2). The test in line 1 of merge sort merge-sort reads quote unquote, if P is greater than or equal to R, rather than scare quotes, if quote unquote, rather than quote unquote, if P is not equal to R. Now, if merge sort is called with P being greater than R, then the array A, open bracket, P colon R, close bracket, is empty. Argue that as long as the initial call merge sort merge-sort open parentheses A comma 1 comma n has n greater than or equal to 1, the test quote unquote if P doesn't equal R, end quote, quote, end quote, yeah, suffices to ensure that no recursive call has P greater than R. Well, so we want to argue that as long as the initial, which is supposed to be 1L, call merge sort with parameters A, 1, and n has n greater than or equal to 1, the test, if P is not equal to R, suffices to ensure that no recursive call has P greater than R. Now, intuitively, we only ever split valid non-empty ranges in half. Both children remain valid ranges with P being less than or equal to R. How do we say this more rigorously, right? So assume the initial call has 1, which is less than or equal to P, which is less than or equal to R, which is equal to n. Now, if P does not equal R, then the code sets Q is equal to the floor function, open parentheses, P plus R, close parentheses, over 2 floor function, in floor function, and recurses on the array, well, open bracket P, colon, Q, close bracket, and open bracket Q plus 1, colon, R. Because P is less than or equal to Q, which is less than R, both satisfy P is less than or equal to R, and are non-empty or singletons. Now, inductively, any call with P less than or equal to R generates children with P is less than or equal to Q, which is less than or equal to R minus 1, and P plus 1 less than or equal to Q plus 1, which is less than or equal to R. So P less than or equal to R persists, and P greater than R never occurs. Therefore, the condition P does not equal R is sufficient for this case. QED, right? So that does it for this argument. Now let's move on to the next exercise. So for exercise 2.3-3, state a loop invariant for the while loop of lines 12 to 18 of the merge procedure. Show how to use it along with the while loops. Of lines 20 to 23 and 24 to 27 to prove that merge is correct. So let's talk about how we do this a bit more intuitively. So at each step, we would place the smallest first element among the two input lists into the output. The prefix that would be written so far is the globally smallest set of elements in sorted order. Okay, that's the intuition. Now how do we say this a bit more rigorously to discuss a sort of main invariant, right? Well, let I, j, index the current heads of the two sorted lists L and R, and let K index the output segment, the array A, open parentheses, P, all the way up to R, close parentheses. What would be the invariant in this case? Well, let me take a drink of this first. Well, the invariant would be at the start of each iteration of lines 12 to 18, which is to say the array, open bracket, from P all the way to K minus 1 contains the open parentheses K minus P close parentheses. It's supposed to be the K minus P smallest elements in the array sorry. Smallest elements of L, open array I, on and on, in union R, to denote the left and right. So array, open bracket, J, on and on, close brackets, in non-decreasing order. And all elements in the array A, open brackets P, all the way to K minus 1, are less than or equal to every element remaining in the array L, I going on, and R, open brackets J, dot dot dot, close brackets. That's what's invariant. Now let's go on to discussing each step in turn from initialization to termination. So with initialization, what we have is that K equals P. So the prefix is empty and trivially sorted. So that's it for the initialization. Now no, getting ahead of myself there. Onto the maintenance. So for the maintenance, the loop compares L, array L, indice, L, open bracket, I, close bracket, and R, so these would be the specific indices, open bracket, J, close bracket, writes smaller to the array indice A, open bracket K, close indice, and advances the corresponding index. This preserves that the output prefix contains exactly the next smallest element and remains sorted. So it can be maintained. The process can be maintained, so that's good. Now let's see about termination. So the loop stops when either list is exhausted. So it's like people in a sense. No, is exhausted. The cleanup loops lines 20 to 23 and 24 to 27 copy the remainder. Let's see if I can. If I had a copy and merge sort with me, I would pull it up. Unfortunately, I do not. Dang it. Because then we could see that more explicitly, right? So I do not. Not in all of my notes, do I? That is a supreme oversight. I mean, merge. I'll write that down for later. So the loop stops when either list is exhausted. The cleanup loops in lines 20 to 23 and lines 24 to 27, those copy the remainder of the non-empty list into A. Since all remaining elements the reason I'm looping the L's is so that they're not mistaken for ones or any sort of other variable. Since all remaining elements are greater than or equal to the last written element, the final array the final array A, open bracket, from P to R, is a stable for horses, no, is a stable sorted merge of two inputs. And so there we go. That is it for exercise 2.3-3. Now, let's go on to exercise 2.3-4. So 2.3-4, let's see that. We're told for this exercise, use mathematical induction to show that when n is greater than or equal to 2 is an exact power of 2, the solution of the recurrence T of n, big T of n, which is about time, so is equal to 2t of n over 2 plus n is t, big T of n, which is equal to n log n. So, how do we go about this intuitively speaking? The recursion tree has log n plus 1 levels with total work n per internal level. Summing that gives n log n plus linear leaves. How do we go about showing that more rigorously, though? Well, let n equal 2 to the m for m greater than or equal to 1. Claim t of 2m is equal to 2 to the m times m. Base m is equal to 1, which would mean n is equal to 2, such that t of 2 is equal to 2t of 1 plus 2, with t of 1 equal to 0, or any constant. So t of 2 is equal to 2, which equals 2 to the 1 times 1. Step. So this is the inductive step here. So we have the base case. Now it's time for the inductive step. Assume t of 2 to the m minus 1 is equal to 2 to the m minus 1, open parentheses, times open parentheses minus 1, close parentheses, then t of 2 to the m, close parentheses, t of 2 to the m is equal to 2 times t of 2 to the m minus 1 plus 2 to the m is equal to 2 times 2 to the m minus 1 times open parentheses m minus 1 close parentheses plus 2 to the m, which is equal to 2 to the m times m minus 1 close parentheses plus 2 to the m, which is equal to 2 to the m times m. Therefore, t of n is equal to n log n for n is equal to 2 to the m. And that's it for 2.3-4. And so let's go on to 2.3-5. Still have some problems problems to go here before we, exercises to go before we reach the actual problems, right? So, for exercise 2.3-5, think of insertion sort as a recursive algorithm to sort the array A open bracket 1 colon and close bracket recursively sort the array A open bracket 1 colon and minus 1 close bracket, and then insert A open bracket n close bracket. Write pseudocode for this recursive version. Give a recurrence relation, a recurrence for its worst case running time. So intuitively, you sort the n-1 items, then bubble the last item left until it lands in place, right? Hence bubble sort in a way, but how do we say this more rigorously, right? So I mentioned bubble sort, but it was a misdirection, a red herring. Because what we really have isn't bubble sort, at least not explicitly. You may see about that. So it's very similar, but it's not quite. So let me just show you. So let's have rec hyphen insertion hyphen sort open parentheses A comma n close parentheses 1 if n is less than or equal to 1 colon return 2 rec. So this is the recursive part here, hyphen insertion hyphen sort open parentheses A comma n-1 close parentheses line 3 key is equal to the array open bracket the array A open bracket n close bracket semicolon here. Not sure if I should really write that because I don't know about the formalities of pseudocode insofar as like semicolons are concerned. Some people are like, oh, that's fine. Other people are like, no, that's definitely not fine. I'm just going to go ahead and put it there and say I is equal to n-1 line 4 while I is greater than or equal to 1 and the array open bracket, the array A open bracket I close bracket is greater than key 5, line 5, the array A, open bracket, I plus 1, close bracket, is equal to the array A, open bracket, I, close bracket, semicolon, I is equal to I minus 1. Now, if you didn't have the semicolons here, or you weren't allowed to use the semicolons, right, you just move this. Just move this part, because this semicolon here is used to indicate a line break. So there we go. And for 6, we have the array A, open bracket, I plus 1, close bracket, is equal to the key. Now, in the worst case, line 4 shifts through the entire sorted prefix comma costing theta of n, that's after a recursive call on n minus 1 elements. So t of n is equal to t of n minus 1 plus theta of n, and all of this is equal to, you probably guessed it, theta of n squared. All right. That's going to be it for today for now. We'll continue on a bit later.